So let's have a look at another example of this, using the substitution to do it. I'm going to do this one slightly differently and then show that the substitution gives the same answer. Because actually, with this example, which is why I picked squared, I could actually multiply out these brackets and then integrate each bit separately. So let's try that. This equals the integral of 6x plus 3 times 6x plus 3 dx. So now I'm going to multiply out the brackets, collect together like terms, and then try and integrate that. So I'll just pause while you try multiplying out the brackets and collecting like terms. So that gives us this, multiplying out the brackets. Now I'm going to integrate this last expression here by using the standard integral, add 1 to the power divided by the new power. So just go through, integrate that, see what you end up with. So hopefully you get that as your integral. This is your final answer here. If we go back to the original integral, we could do that because this is just squared. If you think back to the previous example we had, that was to the power 7. So if this was power 7, then I could multiply out this bracket by this bracket 7 times, but you know, it gets rather long-winded, and this substitution method gives us a shortcut. So I'd always use this substitution method if the power gets more than, say, squared. If it was squared or cubed, I might be tempted just to multiply out, but otherwise I'd use the substitution method. And in fact, once you're used to the substitution method, it's so much quicker really that you might as well use that. Okay? So let's have a look at this substitution method and see if this works and we get the same answer. So the original integral then is the integral of 6x plus 3 squared with respect to x. So what's the first thing we do? So the steps are step u and then differentiate it. So in this case we're going to let u equal the bracket 6x plus 3, and that's commonly the case but not always. And then once I've set what u is, I differentiate it. 6. So that I can express dx in terms of du. So I've just got to now rearrange this little equation to get dx equals du over 6. In other words, I just move the dx up to that side and then bring the 6 down. So that's effectively what we do. Now make the substitution. I'm going to replace 6x plus 3 in here with u, and I'm going to replace dx here with that. So rewrite the integral to making the substitution. So what do you get? So the original integral, 6x plus 3 to the power 2 with respect to x, is replaced by what? Replaced by u squared, the integral of u squared with respect to u over 6, du over 6. What we can do now actually, which we've talked about in the past, because this over 6 is constant, we can take that outside the integral. So I would at this stage actually probably rewrite that as 1 over 6 times the integral of u squared with u. So I take that 6, that number outside of the integral. And now look at that u squared, integral of u squared to u, that's just the standard integral. So I just add 1 to the power divided by the new power and I get so that gives us 1/6 of u cubed over 3. Tidying up, the 3 and the 6 can be multiplied together to give 1/18. So it equals 1 over 18 times u cubed, and u is 2x plus 3, wasn't it? No, 6x plus 3. 6x plus 3 cubed. Or we could write it as 6x plus 3 cubed over 18 plus c. Remember, an 18th is the same as divide by 18. An 18th rather. An 18th is the same as divide by 18. Thinking back to when we were sort of trying to do it almost by looking at it, if we look at the original integral, which is this one here, this is the shortcut, but only use this when you're confident. That's going to be my u, so I just integrate, ignoring what's inside the bracket, I just integrate the bracket effectively to get bracket cubed over 3. But if I differentiate the bracket, I get 6, so I've got 3 times 6 underneath, which is 18, so that you can almost jump straight to that last bit, but only when you're confident. The last thing I want to do with this little exercise is just to show that, of course, that gives this. Is that the same as that? So let's just have a look at that. So does the answer from the substitution method equal the answer by just splitting it up? How would we prove that they were the same? What would you do? To prove this was true, I would multiply out this. 6x plus 3 times 6x plus 3 times 6x plus 3, collect together like terms, and then hopefully show that that equals this. Because that answer will then be divided by 18, this 18, and then you hopefully show that's the same. I'm not going to do that now, I'll leave that as a little exercise for you. If you'd like to, have a go at it. But I want to make the point that look what else the substitution method does for us. If we assume that they are the same, and you'll prove that they are the same. If you don't, then, and you want to, you're not sure why, come and find me and we'll have a look at it. But they are the same, and this actually is a very convenient way of writing the answer. Because if we want to try and solve something with this in it, then we can look for values. If this say equals 0, then what value of x can I find so that this is 0? Well, the bracket will be 0, and so 6x plus 3 equals 0. If I'm trying to solve 1 over 18, 6x plus 3 cubed equals 0, if I'm trying to solve that, find the value of x that gives me that. In this form it's easy, because I can multiply both sides by 18, this will still be 0 on the right, so therefore 6x plus 3 cubed must equal 0. I can find the cube root of both sides, because the cube root of 0 is still 0. So in other words, 6x plus 3 must be 0. Because this is 0 on the right, I can say if that whole lot's 0, then this bit must be 0. And more than that, I can cube root both sides and say that's 0. So all I actually end up having to solve is that little equation to find out what x is. So if somebody asked me to solve this equal to 0, it would be very difficult. But if it's written like this, it's actually trivial. So not only does integration by substitution work as well, it actually gives you the answer in a much more convenient form often.